Thank you all so much for coming, and to Mukesh for the invitation. It's a real pleasure to be down here. You know, I feel like I am sort of coming to the hub of water in the United States, coming to the University of Alabama. So it's terrific to be here, and I'm really excited to tell you all about SWOT, the satellite that I've been working on for, 20 years now. Fundamentally, in my heart, right, they call me a global hydrologist, but fundamentally, there is nothing that I like more than going out into the field and standing next to a river. Ideally, I'm making some kind of measurements of the river, but I'm also standing there thinking about, like, okay, how does this river work? What are the processes that are going on? And, you know, I try to keep a field part of my research portfolio so I can get out there and think about the systems that I work on while I'm standing next to them. I think it's important. But early on in my career, I realized, as many people do, that field measurements on their own weren't going to get me everything that I wanted. I needed something that would get me global, and I'm never going to make global scale field measurements. And so I started thinking about satellites. And people who, you know, I study rivers, and people who, and surface water hydrology in general, and people who study surface water hydrology, we've been using satellites for a really long time. But those satellites have all been pretty much repurposed from other people's primary objectives, right? So we've started with, you know, satellites like Landsat, which, you know, as the name implies, right? It was originally, you know, focused on land resources. And so we've used it to measure things like inundation extent, right? That's not, Landsat wasn't originally designed to measure inundation extent, but gosh, we've been doing that since like the early 1970s. We've taken oceanography satellites like Sentinel-3 or Sentinel-6, which were designed to measure ocean, water levels, sea levels. And we've said, well, hey, you know, if we retrack those data and come up with some novel, you know, workarounds, then we can use those to track water levels in rivers and lakes, and that's great. And then we've used things like GRACE and GRACE follow-on, right? These were originally geodesy missions, and there were like a few hydrologists kind of tacked on to the end of the mission. If you go back to, the late 90s when the first GRACE was being launched. And now it's like, we figured out, okay, we can get all this interesting information about groundwater and total water storage, and it's this key part of global water budgets. And so we've really had this, as surface water hydrologists, we've had to be creative and sort of MacGyver solutions with satellites that weren't designed for our purposes. And so you go back 20 years, and NASA and other space agencies started approaching some surface water hydrologists and said, hey, if we were going to design a satellite for you, what would it need to do? And we kind of came up with, and when I say we, I was a master's student when I went to my first meeting in 2004, so mostly I was sitting there listening. But we as a community came up with 4 things that we wanted to do. So the first thing is we wanted a satellite that could measure the elevation of water surfaces in rivers, lakes, wetlands, and we'll throw the oceans in there as well because they're important, and I'm going to talk about oceanography as well. Right, so for example, we wanted to be able to see like how the volume of a reservoir changes over time, or we wanted to be able to see how sort of the prism of a river changes, right, as water level changes, not just elevation on its own. We wanted something that was going to work broadly, right, in rivers, lakes, oceans, ideally some kinds of wetlands. We wanted something that was going to be global or nearly global, so that we could, we weren't constrained to just certain areas or certain ground tracts. And we wanted it to collect frequent, and I should have added the word enough, frequent enough observations. So what's frequent enough? Well, we're all scientists here or engineers, and frequent, ideally we would have, measurements every minute on the minute everywhere on the globe. But that's not going to happen. So ideally, frequent enough means there are some processes that are really important where we're getting measurements often enough that we can constrain those processes. And so our community took these ideas to NASA and to other space agencies and said, hey, this is what we need. And I am not a satellite engineer. I do not come up with ideas for how to make that work. But fortunately, there are really smart people out there who do come up with ideas for satellites. And one of them is a scientist, engineer, Renaissance person at NASA Jet Propulsion Lab named Ernesto Rodriguez. And he's maybe the only person who I know who can talk to hydrologists and oceanographers and radar engineers all in their own languages and like make major contributions to all of their fields. He's a brilliant guy. He is, however, extraordinarily hard to find a picture of on the internet. And so in order to show you what Ernesto looks like, I had to go back to a photo from my 40th birthday party, which was, it happened to coincide with the SWOT science team meeting in France. And so this is Ernesto right here. And he, back in the late 90s, early 2000s, came up with this idea for a satellite-based instrument that could do everything that we wanted in our sort of wish list. And that instrument he ended up calling KaRin, the Ka-band radar interferometer. So let's unpack what that means and like what's different about KaRin. So the first thing is it's a radar instrument. And it's specifically a Ka-band radar. So these are our different radar bands, right? They're nonsensically named. You just have to memorize them. But most of our satellites, sensors that we've had up, on satellites in the past and what we currently have up there are up there in like long wavelengths. So L-band, C-band, maybe some X-band stuff, right? Where we're talking about like, somewhere between maybe 3 and 30 centimeters. KaRin is very different. It's a Ka-band radar, which is really, really short wavelength, right? So SWOT is actually, or KaRin is actually 0.86 centimeters, so little tiny waves. So that's the first thing that's different about SWOT, is it has this really short wavelength, and that is important because if you work with radar data, you know that radar waves tend to interact with variability that's roughly on the same order of magnitude as the wavelength, right? Or maybe half of that. And so, if we want something to bounce off of water surfaces, reflect off of water surfaces, we need it to be at a wavelength that is maybe comparable to the waves that we're going to get on water surfaces. And so if you think about like a river or a lake, right? Every once in a while, you're going to get big waves on those. But most of the time, the waves are really small. You've got these little capillary waves, right? So we need something that's able to measure those small waves. So that's the first thing that's different about KaRin. The second thing is that most radar systems, if this is our satellite, right, and then this red line is sort of the nadir track, the ground track. Most radar satellites that we've had up there, typical SAR satellites, look off to the side, way off to the side, so like 30 to 50 degrees off nadir. And there's a bunch of information that you can get. I'm not going to go into it by looking way off to the side. It's really useful. But if you look at that image up there, that's of a river in Siberia, and you can see that the river flowing through the middle of that is dark, right? It's black. That means that we're not getting any returns off of that water surface. And part of that is because the wavelengths in this image are very long, but part of it is because we're looking way away from the satellite, so all that energy is just being reflected off, and none of it's coming back to the satellite. So the idea that Ernesto had was, what if we look really close to the satellite instead? And so what SWOT does, or what KaRin does, is it looks 1 to 4 degrees off nadir, so just barely away from the satellite ground track. And if you look at, now this is an image from SWOT, I'm getting ahead of myself a little bit, but over a braided river in New Zealand, and now you can see that the water is bright, right? We're getting returns off of the water surface, and the land is much darker. And so the third thing, which I don't have a slide for, that's different about relative to other satellite-based radar instruments, that it has 2 antennas rather than 1. So it's designed to do interferometry in one pass, which means that it basically can measure elevations every time it goes over, rather than having to do like different images collected at different times in order to back out like changes in water surface elevation. So we'll get to that more in a little bit. So this was a really innovative and different kind of satellite instrument, this KaRin instrument. There's one more thing that I want you to know about KaRin. And for this, we have to go back to that birthday party photo. So this is Ernesto's wife, who is also named KaRin. which I've always thought was kind of sweet. So KaRin ended up, the hydrology community ended up saying, yeah, KaRin is a great idea back in about 2004. And it turns out that the oceanography, the physical oceanography community, had come to the same conclusion. And so those two communities kind of joined forces. And in 2008, we formed the initial stages of what we call the Surface Water and Ocean Topography mission. And so SWOT it's a satellite, so it uses radar interferometry, and it's designed to measure simultaneously inundation, extent, and water surface elevation. As I said, we've been working on it for a really long time. And it finally launched, and we'll talk a little bit more about this, on December 16th, 2022. So it's been up there for about a little more than 2 years now. So if we look at SWOT, the basic geometry of it is a little bit unusual, right? And I talked about this a little bit before. So you have the nadir track is now this sort of brown line, right? So the satellite passes right over the brown line in the middle. But the main measurements that we're getting, we have this like 20-kilometer gap in the middle. And then we've got these two 50-kilometer wide stripes. And in each one of those stripes, essentially we get an image of water surface elevation, so we can see where the water is and how the and what the elevation is. On average, we get an observation about once every 10 days, although that varies a lot with latitude. So as you get to higher latitudes, you get more observations. It covers a big wide swath of the Earth, not the entire thing, but between 78 north and 78 south, which is pretty much all of the lakes and rivers on Earth. The latency ends up becoming important if you want to use SWOT data for any kind of like near real-time applications. And processing this data is a lot. SWOT produces about a terabyte of data a day, and we have to downlink that from the satellite and then do a bunch of pretty heavy processing on it. And so we can't get that data out like right away. It takes us about 3 days to get that data out. And that is a little bit of a limitation for some applications. Nominally, SWOT is supposed to last for about 3.5 years. We're about 2.5 years into that. And so that feels like, okay, we're coming to the end of something here. But NASA has a really long history, and space agencies in general, of under-promising and over-delivering on mission lifetimes, right? So my hope is that SWOT ends up being like the Landsat 5 satellite, which was originally supposed to be a 5-year mission and ended up lasting for 26. But we'll see if we get lucky. The other point that I want to make here is I work a lot with NASA, right? But SWOT is really a mission that is truly international. So CNES, the French space agency, put in about a quarter to a third of the budget for SWOT, and they are really full partners scientifically and technically on this. And then Canada and the UK contributed smaller amounts. And so this mission would not have happened without the input from these international partners, especially France.
What is the rough budget? I mean,
1.2 billion.
1.2 billion?
Yep. Yeah. So this is like a flagship level Earth science mission for NASA. So if we take a look at a nice little mock-up of SWOT that NASA put together here, just to get an idea of how it makes its measurements, you can see the two radar antennas, if this will actually play. All right, we're going to treat this as a series of images. So you can see the radar antennas here. So this is one radar antenna and then the other one is up there. One thing from an engineering perspective, because I know there are a lot of engineers here, SWOT was actually a really hard mission. So NASA put it in, I think, the 86th percentile of all missions that they'd ever done in terms of difficulty. And a lot of the difficulty came from something that you might not expect, which is that these two antennas are separated by a boom. And we need to know the length of that boom. It's 10 meters long, and we need to know the length of that boom in order to do accurate interferometry to about 1 micron. And given the thermal environment of space and mechanical, that's really hard on its own. But then, in order for this to launch, right, we need to fold that boom up. So it needs to be that stable, not just like when it's in its deployed position, but it needs to be able to fold and then be that stable. So that was like the hardest part of building SWOT, was figuring out how to engineer that boom. As I said, SWOT kind of makes two fundamental measurements that we're going to use. And the first one of those measurements is backscatter, right? So this is essentially, and I'm showing you a couple of images. I'm going to come back to this. So backscatter, right? This is essentially, we send a radar pulse out. We measure how much of that energy comes back to the sensor, and that's going to be really instrumental in telling us where water is, right? So, and SWOT, as I said, is designed so that the backscatter is high off of water surfaces. Then the other thing that we're going to measure is phase, right? And this is basically a measurement of timing. And the way interferometry works is essentially through actually, honestly, pretty simple trigonometry, where we have these two antennas, and then we have that 10-meter long baseline that we know really precisely, and then we can measure the difference in timing of when that radar pulse comes back to the two antennas. And from there, we can back out essentially the elevation of the surface very precisely. And so this is an interferogram that you can then transform into water surface elevations. So a bunch of work was put into engineering SWOT and building the satellite, and then we get to 2022, and things start happening. And we were hoping that we could get them to launch, but in December we had the president of France come to NASA headquarters with Vice President Harris, and they were all celebrating the fact that the two countries together had built this amazing satellite mission. And then, we had some delays, so they couldn't actually be at launch. But then December 15th, 2022, it actually should have been the 16th, 3:46 a.m., I was lucky enough that I got to be standing in a field about 8 miles away from this rocket. And let me tell you, if you ever have a chance to go and see a rocket launch in person, do not miss that chance. Even more if you've been working on the payload for the last 20 years and you're there with all the people you've been working on it with. I will say that watching SWOT go up in that rocket, I don't have kids, so my wedding is up here, and then SWOT launch is here in terms of life experiences. So I highly recommend doing that if you can get away with it. Okay, so SWOT launched, and of course we were all nervous. Is it going to go okay? It went great. But then immediately almost you start to think, okay, but is the data going to be any good? And so I'm going to show you the very first image that I ever saw from SWOT. And this was surreptitiously emailed to me under the table because I technically wasn't authorized to see it. What this image is, and let me walk you through it, is basically this was collected over Antarctica. And so you can see it's basically going from this point here over to this point here. And the bottom is that backscatter image. And so I started looking at this image, and I was like, oh my God, this is amazing. So over here we have the ocean, and you can see a bunch of sea ice here, right? So you've got a relatively bright ocean over here. You can see some features in that ocean in the backscatter, and then you can see all a bunch of stuff going on in the sea ice. You can see maybe another area of open ocean over here. And then if you get up on the ice sheet, it's probably a little bit hard to see from out there, but you can see all these structures and features on the surface of the ice sheet here in the backscatter, which is hey, okay, we're seeing real stuff here that we would expect to see. And then that top one is an interferogram, right? And if you don't work with radar interferometry, it might be wow, that's a bunch of sort of slightly psychedelic colors. But basically, each one of those fringes, right, when we go from pink to blue, represents a certain change in elevation. And there's something a little bit weird going on in the middle that I won't get into. But basically, what we're seeing over here is, hey, the ocean is pretty flat. We can see a little bit of variability in it, but it's pretty flat. We get on the ice sheet, we see a whole bunch more signal that we could interpret as topography. So the people who do what we call phase unwrapping to turn this into height data essentially started looking at this and saying, okay, we are in business. We're going to be good to go here. And so the first data that we got that we could really analyze from SWOT wasn't really over rivers and lakes, which is mostly what I work on. It was over the ocean. And that's because SWOT, one of the other innovative engineering feats of SWOT is that it's the first satellite that actually does interferometry in space. So they actually put a computer on the satellite that does interferometric processing on the satellite, and then we only downlink the results of that. And that saves us massive amounts of data downlink capacity, which is one of the main constraints on SWOT. So but mostly that data is only useful over the ocean. So this is the first data from SWOT, or image from SWOT, figure from SWOT, that was actually released to the public in March of 2023. And it's showing the Gulf Stream off of North Carolina. Everything that you see in red is like higher ocean surface elevation, sea surface height anomalies, and anything in blue is lower. And what you're seeing on the left here is what we had before SWOT, right? So if we take all the other satellite data, we can kind of get this pixelated, blocky picture where we can see like big patterns of, it's like, okay, it's a little higher up there, it's a little lower down there. This is what we get from SWOT. And this is pretty zoomed out, right? If you zoom in on this, you can see all kinds of details that you can't even see at this scale. So the way I think about what SWOT is doing for sea surface height is that this is kind of the equivalent of going from like from the Hubble Space Telescope to the James Webb. Or like 7 years ago when I finally gave in and got glasses. And I was like, oh my gosh, okay. So, we start looking at this and it's like, okay, this is going to be really cool. And this is not just cool, over the Gulf Stream. This is cool over the globe. So this is 10 days worth of SWOT data from 2023 globally. In terms of ocean surface elevations, and you can see all kinds of big scale patterns here. But the cool thing is you can zoom in on all of those big scale patterns and see, not just sort of the big patterns of ocean circulation, but then you can see all the little eddies that are spinning off of those down to about 10 kilometers in scale, or actually maybe even finer than that in some cases. So the oceanographers now are doing some cool processing where they're like actually picking out like surface waves, like it's like swell essentially that you would see if you were out in a ship on the ocean. So what we're seeing from SWOT on the ocean is phenomenal. It's being game changing. Actually, if you go back last week, SWOT was the cover story in Nature, and so this is like changing the game for physical oceanographers. But I'm not a physical oceanographer, so let's think about like what is SWOT doing for hydrology, for surface water hydrology. And so the first image that I saw that was actually over like a river from SWOT was also in March of 2023. And it was this image. So this is of the Garonne River in France. And so the city of Toulouse is kind of like right up where that big bend is there. And you look at this, and this is just a backscatter image, so we're not doing anything with heights here yet. But you look at this, and you're like, hey, we can definitely pick out that river really well. And SWOT was originally designed to measure rivers 100 meters wide and wider. So the Garonne itself in Toulouse, I took this picture a few years ago, it's about 200 meters wide. And we can see that great. This little tributary down here, it's about 50 meters wide. Guess what? We can see that really well too. But you come over here, you see this sort of little line that's moving through the image? That is the Canal du Midi, which was built by Louis XIV, under Louis XIV. I don't think he lifted a shovel. And it's about 20 meters wide. And we can see that too. So one of the things that we realized early on with SWOT is that it might actually have capabilities beyond even what we thought it was going to be able to do when we launched it, right? Our requirement was we have to measure 100-meter wide rivers. Our goal was 50-meter wide rivers. And we're seeing things that are 20 meters wide here, which is pretty cool. Okay, so what about seeing, water surface elevations with SWOT? So the first figure that I actually made with SWOT data was over the Yukon-Kuskokwim Delta in Alaska. So it's like far western Alaska. And it combined SWOT data products, which I'll talk about more in a minute, covering rivers and lakes. And so what you're looking at here, the color here is water surface elevation on a log scale from 0 to 100 meters. And the lines that you can see here are a representation of rivers. And this is the Yukon River here, right near its delta, so it's really flat. And if you look at that, it's pretty easy to see that you can pick out the slope of that river from SWOT data, which is pretty extraordinary since it's like less than 10 centimeters per kilometer. It's a really, really flat river. And you look at some of the steeper rivers and you can even more clearly see the slope. The other thing that's interesting to look at are all the lakes that are around in this delta. So this is a very lake-rich region. And we can absolutely see topographic variations that make sense in terms of in terms of the elevation. So we'll talk about validation in a minute. But what blew me away about this image is that I can tell you exactly how many of these lakes we had gauge data for before SWOT. And the answer is 0. Right? And I don't know, I haven't counted how many lakes there are in this image, but there have to be thousands, right? And so now we have the ability to track how water levels vary in all of these lakes. So this is kind of a nice slide to segue into a little segment where I want to talk about SWOT data products, because some of you might be interested in using SWOT data. And it's not like there's just one SWOT data product where you go and download it and you're like, okay, this is what I'm going to work with. So there are actually, for hydrology, we are required to produce all of these different data products. And I'm not going to talk about all of them today, but I'm going to talk about 4 of them. What we call the pixel cloud product, the river single pass product, the lake single pass product, and then the raster product. And I'll sort of walk you through a little bit of how they're produced and what they might be useful for. So let's start with the pixel cloud product, because it is like the foundation of everything else that we do. So before we get to the pixel cloud product, there are other SWOT data products where if you are a radar engineer and you want to go and work in radar coordinate space and do radar processing, you absolutely can do that. The pixel cloud product is the first geolocated product that you can get from SWOT. And it looks something like this. So this is in an area in Eastern California. And essentially, each one of these dots is a place where we have bright enough returns from SWOT, good enough returns from SWOT, where we think we can provide some kind of an elevation and an inundation extent. And so if we zoom in, this is a reservoir over here, and you can see there are all of these different sort of pixels here. And each one of these has an elevation from SWOT associated with it, and an inundation, and a bunch of like quality flags and sort of ancillary data. And so if you wanted to know the elevation of this reservoir, you could take an average of all of those pixels within it. If you wanted to know the inundation extent, you could sum up the areas of all those pixels. You will notice that there's a lot of sort of scattered pixels around all over the place. And this is definitely not the pixel cloud data product is not one where it's like perfectly clean and everything that's in it is a real measurement of a water surface, right? Essentially, we're taking anything that's bright, where we get a bright return from SWOT, and we're saying, great, let's add that in. And the general approach for SWOT is we would rather include data and flag it rather than try to exclude data when that means that we might be getting rid of useful things. And so the first principle, and I'll come back to this, of using SWOT data is you have to do quality filtering. Otherwise, you're going to end up including a bunch of stuff that's actually noise. So in any case, if you look at the colors here, these are water surface elevations, and so we can really clearly see, we're down in a valley over here on the right-hand side of this image, and then those are some lakes up in the Sierra Nevada mountains. There's a little creek that kind of flows down from the mountains down into the valley here, and I don't know how wide that creek is, but a few meters wide. And I look at that and I'm like, I can see that creek in the SWOT data. I bet we could pick something out there, which is pretty cool. Okay, so the pixel cloud data is really great if you're working in a particular area, and you want to do some really intensive processing in that area that doesn't work well with the other SWOT data products. But one pixel cloud granule typically is about a gigabyte, and it only covers about like 60 kilometers by 60 kilometers. And so if you started to try to think about doing analysis of global scale phenomena with the pixel cloud product, you're getting into some really big data analysis really quickly. And so we don't recommend the pixel cloud product for most people who want to work globally. So if you are interested in rivers, we would probably recommend most of the time that the first data product that you should look at is the SWOT River Single Pass, or River SP data products. And so essentially what we do is we take that pixel cloud and we turn it into a vector representation of the river. And so let me walk you through how we do that really quickly. So if you imagine this Carolina blue stripe as a river, we start with the SWOT ground track, right? So imagine SWOT is overpassing from the bottom up towards the top of the screen. And then we're going to get returns off of that river surface, right? And we're going to have pixels that are in the pixel cloud. And what we want to do is we want to turn those pixels into something that's a sort of a more coherent representation of the river. And we're not going to do that from scratch every time, because that's going to lead us with a bunch of these to, let's say, a bunch of lines that are slightly offset from each other. And that's going to be really hard to do, for example, change detection if you have a bunch of unique solutions. So what we do is we actually start with a prior knowledge of where the river center line is. And we say, OK, every time we're going to snap our SWOT data to the same river center line. And what we do is we divide that center line up into about 200-meter spaced nodes. And so each one of those nodes, we're going to take all of the pixels in the pixel cloud that are closest to that node, and we're going to average those or aggregate those pixels to that node. And that's fantastic if what you want to work on is water surface elevations, for example, from SWOT. But if you want to get the slope of the river, right, it's going to be pretty noisy at like a 200-meter spacing. And so we then aggregate those 200-meter nodes up to these approximately 10-kilometer long river reaches. And those reaches have an elevation, an inundation extent, a width, a slope, data quality flags for all of those, correction factors that we apply, and all of that is available. And this is uniquely for satellite data. This is available in shapefile format. And we did that because we wanted these SWOT data to be accessible to, say, GIS professionals or hydrologists who are working out at a company or at a, at agency, and maybe they don't have a ton of experience working with like HDF5 data or something like that, but they can pull a shapefile into QGIS or ArcGIS. And these River SP data are available globally on what we call the SWOT River Database, or SWORD. And so SWORD has about 213,000 total reaches in it. And each one of those reaches, it's 10 kilometers long, there's 200-meter nodes, so there's about 50 nodes per reach, something like that. So you do the math, and we've got something like roughly 10,000 nodes where we have water surface elevations from SWOT. And the colors on this map are just showing how many observations per SWOT's actual repeat cycle is 21 days. And so here you can see as you get to high latitudes, you get way more observations every 21 days. So we actually have, I asked the person who created the SWORD database to tell me what the maximum was. Where do we get the most observations? And there is one river in northern Siberia where we get 34 observations of one reach every 21 days. So if that river is important to you, then you are in luck. OK, so if we actually look at what the SWOT data looks like over some other areas, what does it look like? So I just grabbed one pass of SWOT data, in this case over South America. And so, gosh, that's a little hard to see on the screen. But you can see where that pass is, right? And essentially SWOT overpasses. And unsurprisingly, right, you can see that in the Andes down at the bottom, the elevations are higher, right? Then in the middle of the Amazon basin, they're lower. And then they go up a bit as you get closer to the coast. If we zoom in a little bit on that, right, we start to be able to see the slope of, this is the Tarauacá River in Brazil. I picked it randomly because it worked nicely for the figure. And you can absolutely see, the slope of this river really clearly. If we zoom in even further on that, now you can start to see those individual nodes a little bit. You can also see that, right, we do have errors sometimes. So, for example, like the outside of this meander bend, clearly we have some kind of a problem because it's very unlikely that the elevation of this river is like going up abruptly and then going down abruptly. I think anyone in this room who studies hydraulics knows that's not going to work. So when I look at when I started looking at this data, I said, look, this data looks amazing, but we're not, it's not enough just to look at the data and say, OK, it looks really cool. We need to go out and actually validate the data. And so we conducted a pretty big effort to do that. We went out to all of these places globally and collected field validation data. So this is where I got to go back to standing on river banks, thinking about rivers and making measurements, which was great. And so some of these sites are in rivers, some of them are in lakes. We're working on getting papers out there that sort of present all of this data. We have drafts of one for lakes and one for rivers. I'm just going to show you a little bit of what the validation for rivers looks like today. And the first thing is just to talk a little bit more about sort of the distribution of our river sites and how we did the validation. I could give a whole talk and have given a whole talk just about this. So I'm going to give you the surface level explanation, and then feel free to ask questions. But basically the first thing that we did is the way that we picked our sites is we wanted sites that covered a pretty wide gamut of river widths and river slopes, right? So we wanted steep rivers, and we wanted flat rivers, and we wanted narrow rivers and wide rivers. And so essentially what you're looking at here is just a scatter plot showing all of the river reaches and how they, how they sort of play out in that regard. There are even some more actually that I don't have on here that are in the Amazon that sort of fill in some of the really wide rivers. But you can see that we're covering really flat rivers. Down at the bottom, we have some tidal reaches in there. And then we get up to, I think our steepest river is actually the Waimakere River in New Zealand, which I worked on a bunch, which I think has a slope of 4 meters per kilometer, which is really steep. When I say we collected data, we used a bunch of different methods, but the two main ones we used. First, we went and installed a series of pressure transducers, so water level loggers, in a bunch of these rivers. And this is just an example on the Connecticut River. So each one of these dots is a place where we installed a water level logger. They're colored by which sword reach they fall within. And then basically at each one of them, we surveyed them in with a GNSS system. And so essentially we got an absolute elevation above a geoid that is processed in a way that is absolutely equivalent to the way the SWOT data is processed. And so that's the first thing that we did. The second thing that we did is we essentially took those high precision GNSS instruments, we attached them to boats in various different ways, and we collected long profiles. So we might start up at the very top of this map over here, and by boat go all the way down to the very bottom of this map and collect a continuous profile where we can get an elevation of the water surface. And for the next slide, I'm going to sort of elide all of the processing that we do on this data and go straight to CDFs, where if we take all of these rivers, what do our comparisons against SWOT data look like? And let me explain what these different CDFs are. So on the top row here, we have our node validation. On the bottom is reach. On the left is what we get if we don't do any real filtering of SWOT data. We just filter out things that are outside of the window where we expect SWOT data to work at all. And then if we do a little bit more intelligent filtering, we get what's going on the right. Then the last thing that you should know is that we have two curves on each plot. And the blue curve is the data that you can go download now. And the orange curve is the data that you will be able to go download in 2 weeks when we start releasing it with a whole bunch of algorithm improvements in terms of the data processing. So what do we get out of this? So let's start with nodes, and let's mostly look at where we do some reasonably intelligent data quality filtering. So essentially what we're getting for nodes are, so the benchmark we tend to use is a 68th percentile error. And our 68th percentile error in both of these is about 12 centimeters. Pre-launch, we expected this to be at the node scale to be on the order of 30 centimeters. So this is a lot better than we expected, and we're really excited about it. At the reach scale, there's some more complexity here. So one of the things that you'll notice is that if you look at the blue curve at the node scale, right, which is a lot smaller, naively we would expect if you average over a bigger area, like a whole reach, that you would get higher accuracy. That's not what we were seeing in the data, in the blue curve that where we're currently, of what we're currently able to download. And we think that a lot of that has to do with the fact that once you get to the scale of a whole reach, it's actually really hard to come up with a perfect way of comparing field data to SWOT data. because they're just collected at different scales, right? Your field measurements are either points or lines, and the SWOT data is being collected, over this complex river that's getting wider and narrower and sometimes has multiple channels and things like that. And so we think a lot of the apparent error here is actually just like coming from that difference in what the measurements mean. But in any case, once we get to our higher quality data that's coming out in a couple of weeks, we've got 10 centimeter errors. And this is exactly what our target was. We feel really, really good about it. So SWOT basically is able to measure water surface elevation very accurately. What about slope? Slope we also do really well on. So this is measured now in units of centimeters per kilometer. I'm not going to spend much time on this slide in the interest of time, but basically in the new version, we can measure, our 68th percentile error is 1.6 centimeters per kilometer, which is, that's like getting into Mississippi Delta tidal reach slopes. So we can measure slope very accurately with SWOT. So what are we doing with all this data? So the first thing that I want to talk about briefly is the question, can we estimate discharge from SWOT? And so what we observe with SWOT, right, that's relevant to river discharge is we observe the water surface elevation, right, and how that changes over time. We observe width and how that changes over time. And then we observe slope and how that changes over time. And that's not going to get you all the way to discharge. But if you think about a simple equation like Manning's equation, right? This is a form of Manning's equation. We're getting a lot of relevant information there. So if we reformulate Manning's equation slightly into a form that works for SWOT, essentially everything in black is something that we can measure with SWOT. So we can measure the slope, S, we can measure the width, W, and then if we think about a cross-sectional area, we can measure the change in cross-sectional area over time, even if we can't get some unknown bathymetry that's below what was ever observed. And then we also have no idea what Manning's N is, which is, so I feel like that's always true, right? You can't go measure Manning's N. And then, of course, we don't know discharge. So it seems like we're in trouble because we have one equation and three unknowns. But it turns out that enterprising hydrologists and engineers have come up with a slew of different ways of addressing this problem. Some of them are data assimilation-based. We have some machine learning-based ones. We have some that use what we call mass-conserved flowline version or McFly approaches, where essentially we take Manning's equation. Actually, I have a slide for this. The basic approach is, imagine you have two reaches that are adjacent to each other, right? We can take Manning's equation for each one of those two reaches, and then we can assume that we have mass conservation in between. And so then we have sort of another equation, right? That mass conservation equation. And we can do this multi-temporally. And it turns out that if you start doing this kind of stuff multi-temporally, you can sort of beat down your number of unknowns relative to equations, and you can get it to a place where you can do a pretty good job of inverting for discharge. And so let me show you some evidence of that. So these are a couple of examples. These are, admittedly, places where SWOT discharge works very well. We're still improving it. It doesn't work this well everywhere. But these are a couple of examples. One in France and one in French Guiana, where the in situ discharge is in red and the SWOT discharge is in blue. And so we have lots more work to do, but we are also starting to see these results globally. This is the first global map of discharge from SWOT that I've seen. And so these are all of these rivers and all of these numbers are sort of the average discharge that we think we've seen from SWOT so far. And actually one thing that's sort of fun is that for a lot of these algorithms, for all of these algorithms, we need some kind of a prior. And essentially what you're looking at is what we call the unconstrained SWOT discharge product, where we're not allowed to use anything that is trained at all on gauge data. And so the model that we use for that prior is actually from SEGI. It's WBM. So, okay, let me talk about just a couple more things, and then I'll stop for questions. So discharge isn't the only thing that we can do with rivers. We can also look at what we call spatial hydrographs, right? So we're used to thinking about hydrographs temporally, right? So it's like, okay, you've got a gauge at a point and you look at how discharge changes over time or how water level changes over time. But with SWOT data, and this is some work from George Allen's group at Virginia Tech that was just published in GRL, what they can do is they can actually take the SWOT data and look at how that hydrograph, essentially the elevation of the water surface varies in space. And if they take out sort of a mean, you can see how essentially the shape of the water surface varies over time during a flood, right? So you can see sort of the peak of that flood wave passing through. And they did some really cool stuff where they actually did like hydrograph separation. And this is like base flow separation like we would do traditionally on a gauge. And then up there they've done the same thing, but spatially on a spatial hydrograph. So this is really cool. We can work on rivers. Of course, we can also work on lakes. And so this is the SWOT prior lake database. So just like we have a prior river database, we have a prior lake database. And so we're trying to observe about 6 million lakes worldwide. Essentially, we take this prior lake database and we assign the SWOT data to it. Essentially, these are a bunch of SWOT overpasses over parts of Canada where we're seeing elevations of different lakes, right? So all of the different colors here are different lake elevations. And you can see we're seeing really big lakes, but we're also seeing a bunch of smaller lakes. We can see all kinds of really cool stuff. And so what scientists are doing then, and this is stuff that's been led by Jita Wang, is they're taking these global lake observations. And there's about 5.3 million lakes on this image. So this is just like the average elevation of 5.3 million lakes and reservoirs. And we're just starting at the very beginning of our analysis of this data. But one of the things that Jita's done that's really cool is he's separated those lakes and reservoirs out into lakes where we control the water surface, so reservoirs and lakes where we've built dams, and those that are more natural. And he's looked at like, okay, of the total storage variation, how much is coming from the reservoirs versus the natural lakes. And so the reservoirs are in red on here and the natural lakes are in blue. And it turns out that something like half of all the storage variation in water in the world's lakes, at least the SWOT observable ones, is coming from these very small number of... So the last thing I want to talk about, and then I want to leave a little bit of time for question, is there is a raster data product from SWOT. It's great. We just take the pixel cloud and we grid it to either 100 meters or 250 meters. And this is great if you want to look at a wetland environment. Like this is a big wetland in Colombia. And there's no way you're going to be able to represent this well with the vector data product. But if you want to understand what's going on in this environment, you can definitely look at the raster data product, and it can help you figure out, like, okay, what direction are things flowing in this complex environment hydrologically. And so this raster data product is great for that. It's also great for looking at floods. And so actually the last thing I'm going to show you is we did some work on a flood down in Brazil. This was work that was led by a postdoc at Cornell that I was involved in. And so what you're looking at here is sort of a pre-flood image that shows sort of the extent of this river, and this is the city of Porto Alegre right there. And then we were lucky and we happened to capture the peak of this flood event with SWOT. And what we did is we took the water surface elevations and then a really accurate digital elevation model to figure out what the depth of the flood water was over this entire area. And so that's what you're looking at here. So I actually covered up the scale with this photo, but basically darker colors are deeper here. And so this is exactly the kind of thing that you would get out of like a 2D flood model, right? Yep. And we're able to actually observe it with SWOT. Like there's no modeling involved in this at all other than the DEM that we're subtracting from it. And so what we're hoping to do is to take this and turn it into ways to better validate flood models. So I could go on and talk about other things that we're doing with SWOT, but I think I'm actually going to stop there and leave a few minutes for questions.